All right, here we go. I promised I'd write up some slides to describe for you guys how to create free body diagrams, and so here we are. First, I want to remind you what the basic steps for free body diagrams are. The first thing you need to do is to identify and draw a free body diagram for each interesting object. So obviously you need to know what the interesting objects are going to be. This is an art form that requires practice. So you just sort of have to try multiple times and keep solving problems until you develop a knack for identifying which objects are going to be interesting or helpful, which objects are helpful to identify as interesting. Okay, once you've got the interesting objects, you want to identify all the forces acting on each object. This is, again, a skill that requires some practice, but once you've done it a few times, you should be competent. Go ahead and draw a heavy outline for the object of interest. So basically, you're going to need a free body diagram for each interesting object. And let's say we pick object 1, we're going to draw it in a heavy outline, and then for that free body diagram, you're going to draw a dotted outline for the other objects that aren't the object you're focusing on at the moment, but are still interacting with the object you're focusing on. You're going to draw a force for each, you're going to draw a vector for each force acting on the object, with its tail starting at the point of application. Additionally, I'd like you to indicate on the vector the source of the force, in other words, the thing that's causing the force, in addition to an identifier for the object upon which the force is acting. And we'll see how that works here in a minute. Once you've drawn all the free body diagrams, you need to choose a coordinate system and sketch the axes. This will communicate to anybody who's looking at your free body diagram that you have chosen a particular coordinate system and that you're going to use that coordinate system when you reduce this free body diagram to equations. You don't want to draw vectors for forces acting on other objects. Just draw vectors for forces acting on the object of interest. You don't want to include acceleration or velocity vectors as a force because they're not forces. Those are kinematical variables that describe motion, but they're not forces. You remember that forces have sources, so indicate on each vector the source of the force. And then finally, once you've got the free body diagrams, you can write out Newton's second law in vector form and in component form for each of the free body diagram. This will, once you've got Newton's second law written, this will reduce the problem to a set of equations, which you can then proceed to solve. That's the idea. So let's take an example. Let's look at the two books that we talked about in class, Book A and Book B. And let's draw a free body diagram for each of those books. So first, let's focus on Book A. So Book A is going to be a bold picture. Book B and the floor are going to be dotted or grayed out so that we know that you're focusing on Book A. Then let's identify some forces. Well, first of all, we've got the force of the hand pushing on Book A. Then we've got the force of Book B pushing back on Book A. Then, of course, the table is pushing up on Book A, and the earth is pulling down on Book A. So there are 4 forces acting on Book A. I want you to notice that each of those forces has a different source, a very definite source, and also they all act on Book A. So this is a free body diagram for Book A. Then we're going to draw a free body diagram for Book B. Now Book A becomes a dotted sort of shadowy thing, and the floor is dotted and shadowy. And we identify the forces acting on Book A. First of all, Book B. Book A is pushing on Book B. The earth is pulling down on Book B, and the table is pushing up on Book B. So there's only 3 forces acting on Book B. Notice that all the forces act on the same object, and each of them has a well-defined source. So those are the 2 free body diagrams for Book A and Book B. Those are the 2 interesting objects in this problem. And finally, I'm just going to indicate to anyone who is inspecting my free body diagrams or reviewing my free body diagrams that I'm choosing the X direction to be horizontal and the Y direction to be vertical. So then we can focus on the free body diagram for book A, and let's write out Newton's second law in vector form for book A. So what is Newton's second law? It says the sum of all the forces acting on book A is equal to the mass of book A times the acceleration of book A. So it's going to look like this. It's the sum of all the four vectors, those four forces, is equal to the mass of book A times the acceleration of book A. Now what I want to do is to break that vector equation down into two component equations, the x component and the y component. Notice that for each force in Newton's second law, I'm going to get the x component of that force and the y component of that force. So the force of book B on book A points in the negative x direction, and it has a label FB on A. The weight of the book A, the force of the Earth acting on book A, has no x component, so its x component is 0. Then the force of the hand on book A pushes in the positive x direction, so it comes in with a plus sign. And the force of the table acting on book A has no x component, so it gets a 0 in this equation. Finally, the acceleration, we expect the books to accelerate to the right, because that's the way the hand is pushing. So the acceleration of book A has a positive x component. The y components are quite simple. The only vectors with y components are the weight and the normal force, and the weight comes in with a minus sign, the normal force has a plus sign, and so that's all there is to it. Okay, let's look at book B. Remember, with book B there were three forces acting. Again, we're going to write out Newton's second law in vector form. The force of book A on book B, the force of the Earth acting on book B, and the force of the table acting on book B, all added together, is equal to the mass of book B times the acceleration of book B. Now I need to break that vector equation down into x and y components. So I've got the x component of the force of book A on book B, the weight and the normal force. Each of them only points vertically, so they have no x component. And then that gives me that the sum of those three is equal to the mass of book B times the acceleration of book B. The y component is similar, except here we have no acceleration in the y direction. And the force of book A on book B has no y component. The only forces with y components are the normal force and the force of the Earth pulling down on book B. Okay, so let's bring these equations together, the equations from book B, the equations from book A, and see what we can deduce. First of all, from the y component of book B, notice that we can solve for the normal force. The normal force of the table pushing up on book B is just equal to the magnitude of the weight of book B, and that's just equal to the mass of book B times g. And the y component of the book A equation similarly permits us to compute the normal force acting on book A from the table. I want you to be careful. In many situations when there's no vertical motion, the normal force ends up being equal to the weight. But don't fall in love with that, because there are many situations where there is acceleration in the vertical direction, and in those situations this is not true. You need to let Newton's second law tell you what the normal force is. You don't ever assume normal forces or tensions are equal to weight, just because sometimes they are. They aren't always, so you need to pay attention to that. Okay, what about these accelerations? Acceleration of B and acceleration of A? Well, it turns out they've got to be the same, because the two bodies are in contact. If book A moves to the right, book B must also move to the right by the same amount. Therefore, they have to have the same acceleration. Also, we know Newton's third law tells us that the force of book A on book B and the force of book B back on book A have to be equal in magnitude, and therefore we can replace the magnitudes of those forces with a single magnitude, the force, I call it the force of interaction, F sub I. Now, if you go back up and look at the first equation at the top of the page, you'll notice that the force of interaction is nothing other than the mass of book B times its acceleration, which we're now just going to call A. There's no need for subscripts since they have the same acceleration. And I can put that force of interaction back into the third equation in place of the force of book B on book A. And you get that minus the interaction force plus the force of the hand on book A is equal to the mass of book A times the acceleration. Notice this just says the net force in the horizontal direction acting on book A is equal to its mass times its acceleration. But then I can use this to proceed to replace the interaction force with the mass of book B times its acceleration. Then I can move the minus MBA over to the other side and solve for the force of the hand on A. It's equal to the sum of the masses times the acceleration. And I can then solve for the acceleration in terms of the force of the hand and the mass of the two books. So that's the way it works. You write free body diagrams for all the interesting objects. You write out Newton's second law for each free body diagram. You break Newton's second law as a vector equation into two component equations, and then you can make all kinds of deductions based on that. Let's look at the board work problem from last time with the two gliders and the airplane. You're given an acceleration. You're asked to find the thrust of the tow plane's propeller, the force of the propeller on the plane, the tension in each tow rope, and the net force on the first glider. So those are the three things you're asked to find. The way you do it is to write a free body diagram. We can identify the tension in the first tow rope as T1, the tension in the second tow rope is T2. We've got our tow plane and our two gliders. Let's first draw a free body diagram for the tow plane. I'll skip the individual steps, but basically we've got four forces acting on the tow plane. There's a force P, which is the propeller acting on the plane. There's T sub G1, which is the glider 1 pulling back on the tow plane. We've got the earth pulling down on the tow plane and the ground pushing up on the tow plane. Those are the four forces acting on the tow plane. We've got the first glider. What has it got? It's got a tension pulling from the plane, the tow plane, onto glider 1. It's got the tension in the rope connecting glider 2 to glider 1. It's got the normal force from the ground acting on glider 1, and it's got the earth pulling down on glider 1 as a weight. Finally, we've got a free body diagram for the last glider. What forces are acting on it? There's a tension from glider 1 acting on glider 2. There's the normal force from the ground acting on glider 2, and there's the weight, the earth, pulling down on glider 2. Those are our three interesting bodies, and those are the three corresponding free body diagrams. Now let's focus on the plane. First of all, I didn't draw a coordinate system. I should have, but there's a coordinate system corresponding to this picture. If I choose the x direction to be horizontal and the y direction to be vertical, I should include a coordinate system. Let's look at Newton's second law for this guy. It says that the sum of all those four forces, the propeller force, the ground force, the earth force, and the tension in the first tow rope force, are all acting on the tow plane, and the sum of those four forces must be equal to the mass of the tow plane times its acceleration. Let's write out the x component of each of those forces. First, the propeller force acts in the positive x direction. The normal force, the force of the ground pushing up, has no x component. The force of the earth pulling down has no x component. And finally, the tension in the tow rope connecting glider 1 to the tow plane we've gave that a name of T1, and it's negative, indicating that it points in the minus x direction. Those added together must be equal to the mass of the tow plane times the tow plane's acceleration. And in the y direction, the propeller force has no y component. The normal force is positive. The weight is negative. It's equal to the mass of the tow plane times the acceleration of gravity. And the tension force has no y component. And those have to add up to what? Well, the tow plane's accelerating only in the x direction, so the y component of acceleration must be 0. So I'll put in a 0 for that. So it's important when you're filling in the acceleration to think about the two components of acceleration and which way what values they each have. Good. Now let's go back to glider 1. Glider 1 also has 4 forces acting on it. So when we write out Newton's second law of motion, we're going to write it as the sum of those 4 forces is equal to the mass of glider 1 times the acceleration of glider 1. Again, we're going to break each of those forces and that acceleration into x and y components and write out Newton's second law in component form. Now, why would T, the tension of the plane pulling on glider 1, be plus T1? Well, that tension points to the right. The normal force from the ground has no x component. The force of the earth pulling down has no x component. And the tension from glider 2 pulling back on glider 1, we call that tension T2. So it's minus T2 in the x direction. And that's equal to the mass of glider 1 times the acceleration of glider 1. In the y direction, the T1 has no y component. The normal force is positive. The weight of glider 1 is negative, and it points down in the y direction. It's got a magnitude of m, the mass of glider 1 times g. And of course, the tension from the other glider, glider 2, is only in the x direction. It has no y component. And finally, what about the acceleration? The y component of acceleration for glider 1, if it's just rolling along the ground, it's got to be 0. Okay, let's look at glider 2. Glider 2 only has 3 forces acting on it. I'm ignoring any kind of drag or any kind of friction between the gliders and the ground. Those 3 forces are the normal force from the ground pushing up, the earth pulling down with a weight, and the tension force from glider 1 acting on glider 2. The sum of those 3 forces has to be the mass of glider 2 times the acceleration of glider 2. So breaking those down into x components, the normal force has no x component, the weight has no x component, the tension between glider 1 and glider 2, we gave that a name, it's called T2. And it's positive in this case because it points in the plus x direction. That has to be equal to the mass of glider 2 times its acceleration. Finally, in the y direction, we've got the normal force acting on glider 2, we've got the weight of glider 2, that's the mass of glider 2 times g, and the tension has no y component. Finally, the acceleration in the y direction is 0 since there's no vertical motion, so those have to add up to 0. Good. So in this problem, the fact that the normal forces are all equal to the weight is a consequence of the condition of no vertical acceleration. And since we're not including any friction, it turns out the normal forces don't really have any impact on the x direction. So we can forget about the y components for this problem. Later, when we get to friction, we're going to find out that normal forces do affect horizontal motion, and we won't be able to leave out the y equations. But let's just pull out the x equations and then check our variables. First of all, for the tow plane, there are only 2 forces in the x direction, the force from the propeller and the tension of the first tow rope. For glider 1, there are only 2 forces in the x direction, the tension of the first tow rope, the tension of the second tow rope. And finally, for the second glider, there's only 1 force in the x direction, that's the tension of the second tow rope. Now what about these 3 accelerations? The acceleration of the plane, the acceleration of glider 1, and the acceleration of glider 2. Right, they have to be the same. They're all tied together. I'm assuming these ropes are not elastic. They don't stretch very much. So if the plane is moving at so many meters per second, then both of the gliders have to be moving at the same speed. Therefore, if the plane speeds up at a certain rate, the 2 gliders have to speed up at the same rate. So that means that these 3 accelerations are all equal, and we can just call them A. Okay? Since we're given A in the problem, this particular problem gave us A of 1.9 meters per second squared, that means we can deduce everything else from that. We know, for example, T2 is the mass of glider 2 times A. We know that T1 is the sum of the mass of glider 1 times A plus the mass of glider 2 times A. I can get that from the second equation. And finally, from the top equation, I can calculate the force of the propeller on the tow plane. It's got to be the sum of the 3 masses times A. So, and we can compute those because we know the mass of glider 2, we know the mass of glider 1, and we know the mass of the tow plane. So those are the three things we needed to calculate. I think we also needed the net force on glider 1, and of course that's got to be the 310 kilograms times 1.9 meters per second squared, or 1,083 newtons minus 494 newtons. The force on the tow plane from the propeller is 5,263 newtons, and the force on this in the second tow rope is 494 newtons. So we get everything from that. And that's just an example of a problem worked out. Of course, many times you might be given the force of the propeller and asked to find the acceleration. But you can see from the bottom equation, you could factor out the acceleration, divide the force of the propeller by the sum of the three masses, and that would give you the acceleration. Then you could go back to the other two equations to find the tensions in the two tow ropes. So once you've written all these equations out, assuming you know something, you can generally work out the rest. I hope that helps. We'll see you next time.